right, morning, everybody. All right, so I'm Ben. I've been working on OpenBMC for Facebook for the last 2.5 years. So I think some of you will probably hear yesterday, heard my presentation on the NIT management and monitoring. So here's where I talked about a little bit about how we use PLDM in OpenBMC for sensor monitoring and also for our NIT firmware upgrade in our production fleet. So here's a follow-up presentation from yesterday where I'll go into more details on how we perform firmware update through out-of-band using PLDM. Okay. So here's a recap. So the PLDM essentially, it's not the only way to do firmware update, but essentially it's a DMTF standard, which gives us a standard way for both from BMC and device point of view. It provides a standard protocol to do firmware upgrades. Okay, so it defines a protocol, and then we both device and BMC can follow. So if we look at the PLDM, essentially it's so on the bottom layer we have a physical layer, which is your physical link, and then you have in our case we run PLDM over NCSI. So this is what the full stack looks like. You have a physical layer in the bottom, and transport layer can be Ethernet in our case. And on top of it, we have the NCSI control packet. And then there's the PLDM base, which defines how we carry PLDM traffic over NCSI. And then once we have that defined, then you can run PLDM monitoring control or PLDM update over NCSI. Okay, and then PLDM can work for other medium, such as MCTP. But for our use case, I'll just focus on NCSI for now. And for our purpose, we have command line utility, NCSI UTO. So I introduced this a little bit yesterday, where this allows user to send any NCSI command or PLDM commands to a device. And we further extend this for PLDM update purpose. So addition to send raw commands, this will recognize a PLDM package, and it will parse the PLDM package and then do all the orchestration and upgrade. So this I'll show in a few minutes. Okay, so so here's more details on the PLDM over NCSI. So essentially, we have a normal Ethernet frame up to normal Ethernet frame and a special type identifier to identify this is a NCSI control packet. So, and then once in NCSI control packet, there is a certain NCSI command which allow us to carry PLDM traffic. So in this case, the PLDM payload is limited by the Ethernet frame size. So the total NCSI can be 1,500 bytes. So in this case, the PLDM payload can be something like 1476, or basically it's limited by Ethernet frame. And if you run PLDM over other medium, so the maximum size will be different. Okay, so here's this is the PLDM firmware update protocol as defined by DMTF. So essentially for firmware update, both BMC and device can send command to each other. Okay, so and both BMC and device need to keep track which state we are in. So here I try to color code a little bit to help us walk through this. So essentially, even though both BMC and device can send command to each other, we can actually, for my own understanding, I try to divide this into two parts. Okay, the first part is the orchestration. So the first part is BMC will send command to device, informing device, hey, we are about to initiate update. And then both sides, there's some handshake to discover how many firmware components are there in a device, what's the component size, and then what's the maximum buffer we can support. So this is like, this handshake happens as part of a BMC orchestration. Once this is done, BMC goes into listen mode. So now device takes over. Device will start requesting buffers one by one. So even though in theory, both sides can send command to each other at any given time, normally to make forward progress, during the first half, BMC runs the show. So BMC sends the command to initiate transfer. But once we agreed we are in a transfer mode, BMC just sits back and lists and handles all the incoming PLDM commands. Okay, so I'll show how this goes. So initially we start in idle state. So we're in idle state. Both BMC and device are in the idle state. Then BMC sends a command to the device to request update. Oh, by the way, so in any of these states, so I think this diagram looks more complicated because at any state, both sides can decide, well, I want to cancel the upgrade process. So this is very easy on the BMC side. For BMC side to cancel upgrade, we just send the cancel command and it will be done. Device can also cancel the upgrade process anytime. But for device to do it, essentially device just return error code in any of the command that BMC sent. Then we'll go back to idle state. So assuming there's no cancellation, there's no abort, then we start from idle. BMC sends a command to request update. Now both device and BMC goes to a net state. We are in the learn component state. So every PLDM package can contain multiple firmware components. So let's say on your device, if you have 5 distinct firmware components, you can put them in the same PLDM package. And in the PLDM header, it will describe these component types. So once we're in learn component states, BMC send data to the device describing what's the component I'm about to update and what's the size of the component. And so basically provides the metadata to a device. Okay, so once this is done, we're in a ready transfer state. Then BMC sends another command to say, okay, start updating process. So up to this time, notice how device does not send any command to BMC. It's strictly one way, right? BMC sends command to device and we advance state. And once we're in the download state, this is when device takes over. So technically, BMC can still send command at this stage to say cancel transfer, or there's some exceptions. But most of the time, once we reach this stage, BMC just listens. BMC waits for the device commands. So in this case, we will have already agreed on what's the chunk size per transfer. So let's say you have a 10 megabyte firmware, you can decide what's the maximum buffer size that it will support. So in this case, device sends command to BMC to say, hey, give me 1 KB from offset 0. So BMC responds, and then send me next chunk, and next chunk, and next chunk. So right here, device takes over, and device try to dictate when it's ready to receive the next data transfer. So BMC sits idle, and anytime, so actually here, the device sends a command to BMC requesting both the device request a chunk transfer and specify both the buffer size and also the offset. So there is actually no requirement for device to do this sequentially. So from what I see, it's useful on the BMC side to keep track of all the offset that device has requested. Because we have seen cases where, out of a 10 megabyte transfer, device actually misses a few chunks. So at the end, you'll see a verification fail or signature check fail. And if BMC side we can keep track of how many chunks has been requested by device and what's the offset, it will be much easier to debug down the road. Okay, so assuming there's no issues, so device keep requesting additional chunks. Finally, when device receives the entire firmware component, by the way, BMC has no control over this. So out of a 10 megabyte component, device can request 3 megabyte, and device can decide to move to the next state, for example. So it's up to the device to verify this. BMC actually has no way to initiate retry or verify. So we trust device firmware knows what it's doing. So okay, device moved to the next state, and then we are in the verify state. In the verify state, this is all done on the device side. So device will verify the firmware it downloaded is correct, it matches its expectation, it passes the CRC, it passes the signature check. And then once that's done, device will send a command to BMC, let BMC know the state. So if verification is good, we go to the apply state. So apply actually doesn't mean activate. So the apply, I think here you'll see 2 different states. There's apply and there's activation. So apply is implementation dependent. It can be no up on device side, but essentially what this tells the BMC is this firmware has been verified and we are good to go. But it doesn't mean it's been activated yet. So okay, we go to next state, apply complete. Then we go back to ready transfer state. The reason we go to ready transfer and not go to activation just yet is because the PLDM package can contain multiple components. So this is actually a bit loop where we can upgrade, let's say, multiple components continuously. Right, so what we did is we went through a loop once, we update one component. And my current case, most PLDM package I see contains one firmware component anyway. But the spec does allow multiple components in the PLDM package. So in theory, you can keep going through this loop, updating all the firmware components in a device. And finally, when all components has been updated, BMC sends a command to a device to say activate. So this is controlled by the BMC. So from here, so once we are in the ready transfer state, BMC can decide if I want to update other components or not. Or BMC can actually stop the process to say, okay, let's activate what we have. So on the activation, also there's certain options in activate. So in most cases, we want delay activation, which means we send activate command to the device, but it doesn't mean firmware is activate right away. Usually, it gets activated on the next power cycle, for example. But essentially, we have a pending firmware that's ready to be activated. And yep, that's it. So if there's no error from activation command, then we know the new firmware is ready to go. Okay, so here are some numbers. So we tried this in our fleet for the NIT firmware. So actually, with the new kernel, so the time it takes for about 4 megabytes is about 2 minutes with the latest kernel. So this is PLDM over NCSI over Netlink. So it takes about 2 minutes to do a 4 megabyte. And this is actually done through 512-byte buffer per PLDM transfer. So this number can actually go up because earlier I mentioned we can support up to something like close to 1500 byte per transfer, right? But this is up to the device firmware. So when I was doing this experiment, the device I use only supports up to 512 byte per transfer. So that's how I got this 2-minute number. So if we can use a higher buffer, larger buffer, say 1K or even 1.5K, I see this number reduced even further. So and I tried both in-band and out of band. Performance are very similar. Yep, and then here's so here is a demo of this in action. Oh, whoops. All right, 1 sec. The NCSI util I showed yesterday, where we can send just any PLDM comments. So I made sure the device is not in update mode right now. So this is one of the PLDM package which I CP to our BMC earlier. Yep, that's it. So transfer, and anytime I can cancel it, then so the first time I canceled it, notice how it would report success because I was in the middle of an update. I canceled it. If I try it again, it will tell me, hey, you're not in update mode, so there's no cancel update. And we can let it run finish, but essentially right now you can see how device is just requesting buffer, and then right now we're doing 512 bytes at a time, and so this whole thing takes about 2 minutes to finish. But yep. So yeah, that's it. And any questions on the update process? Yeah.
Are you seeing a lot of network controller vendors who are publishing PLDM format firmware updates?
Yeah, so yeah, that's a good point. So I think this is relatively new, especially PLDM over NCSI. So far, the vendors, the network controller vendors I worked with, they both support this. So, but it's new. So when they initially support this, require some integration on BMC side to make sure, like, to debug. But I do see support in the industry. At least the vendors I work with, they all support this. So this is what we use in a fleet for the to push out new NIT firmware. Yeah, it's yeah.
After applied, BMC sends a cancel.
Yeah, that's the point. That's a good point. So the question is, what happens after we hit apply and BMC hit cancel? So actually, that's what I'm doing right now. So here, because I'm updating a test firmware, so it should be almost done. So if we do cancel as long as we don't activate, the new firmware doesn't take effect. So you can actually cancel any time before we hit the activation stage. So that's what happened here. So yeah, ignore the error message. But so right now we are in the apply complete. So I haven't activated the firmware yet. So it took about 2 minutes to go through the whole process, and we are in the apply complete stage. Then here, I can cancel anytime, and then the new firmware won't take effect. Yeah. Cool. Okay. All right. Thank you, everybody.